My name is Ugo Meza,
I am Josh Nabity.
I'm Riga Kier.
I'm Serge Desai.
and we are with the IMSC department here at Iowa State University for our IE 441 Senior Capstone Design Project. Sapphire crystal and fiber optic research was conducted for a steel manufacturing company. The objective of this project was to investigate the survival capabilities of sapphire crystal and fibers while immersing molten steel at an operating temperature of 1650 degrees Celsius, followed by evaluating the rate of degradation for the physical, chemical, and optical properties. The ultimate goal of this project is to develop a new technology allowing for continuous temperature measurements of molten steel in an electric arc furnace. The current method used is an interrupted process, meaning that production must be temporarily halted in order to conduct the temperature measurement. The devices used to complete the measurements are consumable thermocouple probes and are only good for one-time use, with an average of 2.5 interruptions per heat produced. This process is time-consuming, costly, and lacks optimal quality control.
To get in-depth information on the physical and chemical properties of sapphire material, we spoke to the company, suppliers of the sapphire material, and various faculty members at Iowa State. Based on their expertise and our independent research, we came up with two parameters to be measured. The first one was change in diameter and chemical composition of the crystal rod using scanning electron microscope. And then the second one was change in microstructure and composition of the fiber using Raman spectroscopy. Materials involved in these trials were 4 single crystal synthetic sapphire rods, each with a diameter of 5 mm and length of 1 inch. We were also provided with sapphire fiber, which was multi-mode and of 300 micron diameter, and length was 80 centimeter. It was then cut into 4 segments for each of our trials. Our company also provided us with recycled steel, dimensions of which were determined by calculating thermal expansion of the steel.
In the process of conducting this experiment, 5 trials were attempted before having success. The first 4 trials resulted in the crucible cracking, which was most likely due to thermal shock. The crucibles that were used were hard-fired alumina for the first 2, molite for the third, sintered alumina for the fourth, and the successful 5th trial was performed using a graphite crucible. The 5th trial allowed for the crystal materials to be submerged for 1 hour at a temperature of 1665 degrees Celsius. With our successful trial, we were able to draw some results on the feasibility of these materials in a molten steel environment. After being removed from the molten steel, the crystal suffered from internal fractures, but showed no change in diameter. However, the chemical composition on the surface of the crystal showed a change. The fiber did not give any indication that its microstructure had changed, but the results did show that a foreign material was on the surface, similar to what we had seen on the crystal. This foreign material present are most likely due to residual molten steel on the materials.
Given that the company produces 25 heats of steel per day at an average of 37 minutes per heat, the company estimates an additional revenue of $4 million by shortening the cycle time of the heat by 1 minute. As shown by our results, we believe the crystal is unable to survive these conditions. Gradually heating these crystals or applying a coating such as magnesium oxide may improve the survivability, but this would require more testing. As for the fiber, we believe that it may survive the EAF conditions. This, however, could be improved, expanded, and elaborated upon by performing an optical transmission test.